I am Charlie, and I am doing a project that I use SAS Enterprise Miner and helped answer the question, how are individual lifts and attributes driving powerlifting totals? So just to get into it, some background is, well, how can we predict lifting totals using a combo of variables? And which models are best for quantitative or qualitative variables. I came up with two sets of models using SAS Enterprise Miner, because obviously if you are comparing your squat, your deadlift, and your bench to what your total would be, that is the most predictive of what your actual total would be. However, I also wanted to see how equipment, gender, and nationality, even body weight factored into that as well. So some of these qualitative variables that I was looking into are, performance enhancing drug tests and equipment, genders, and the actual dates, because as time goes on, I'm sure people lift more weight than they have in the past. And the more equipment people are using that's specialized to help with lifting, the more they're going to lift. And performance enhancing drugs such as steroids, human growth hormone, obviously might have a huge impact on what people are able to do, since naturally people are able to lift less. So summarizing the data, I got all of this data from openpowerlifting.org, where it aggregates a whole bunch of 2.5 million observations of actual powerlifting competition results. It will show one row. In each row, it will show the full spectrum of the attributes that make up the powerlifting total. So all nominal variables were put into binary columns, meaning if we have categorical variables, instead of representing them by their name, we create separate columns that are designated by 0 being the lack of that attribute and 1 being the presence of that attribute. This helps with being able to actually make regression models and other models that are similar, except for decision trees. As I said, there's 2.5 million rows of data. Unfortunately, SAS Enterprise kept crashing when I tried to roll that in. So our sample size is 1,000 randomly sampled rows from that 2.5 million row source. I allocated 70% of this to be training data and 30% to be validation data, which comes out to 700 and 300, I guess, data points respectively. There are 16 variables, 6 are interval, 10 are binary, and we have one target variable, which is obviously the total weight lifted in kilograms, which is the powerlifting total between squat, bench, and deadlift. Going into the variables themselves, we have male, where it's male equals 1, female equals 0. Not trying to be sexist, it's just that's what I had to put in there to get a result. I could have done it the opposite way as well, and it would have worked the same, but have the inverse number in the models. Multiply designates that there are 2 layers of equipment or more that are permitted. That's if you have like a squat shirt, bench shirt, wraps, straps, all that fun stuff. Raw, obviously no equipment. Straps are lifting straps that go on your wrist and they help increase your grip. Unlimited, all equipment is permitted. That's where you're going to see the largest lifts. Wraps are tight cloth wraps that you wrap around your joints so that your joints stay in place and you can lift more. Body weight is in kilograms. That's self-explanatory. Body weight of the lifters. Then there's obviously the best of 3 for squat, bench, and deadlift, and that's in kilograms as well. And the total is the aggregate between those 3. We also have not tested for performance enhancing drugs, essentially meaning that it is possible to compete using performance enhancing drugs, where 1 is that performance enhancing drugs are permissible, even if they happen to be illegal, and 0 being that they are not permissible. And the year, obviously the year that the lift took place. So I had to do 2 sets of models, as I mentioned. The main difference between those is the presence of the best of 3 bench, deadlift, and squat attributes. Model 2 omits all of these because, as you will soon find out, predicting a lifting total using those 3 attributes is obviously way more applicable than just using separate variables such as lifting straps, gender, performance enhancing drug use. So I did these 2 sets of models just so that we could separately in this model look at all of these variables instead of just these. Here we have the actual diagram that I used. File import goes to data partition. The 70-30 split happens there. Then we go in all the models. We got stepwise regression, which is great for, actually looking at what the results are and interpreting it. We have regression, same deal there. A decision tree, which is super applicable. It helps kind of break down what makes these ideal baskets for a lifter. We also have a neural network that might see things that normal humans can't really put into a model. And then the model comparison node over here to compare each model. So the diagrams are the same for both, but the inputs and outputs do differ for each one. The variable distributions are generally normal. There is some skew in the year since, of course, these powerlifting competitions have become more prevalent as of 2015. As time goes on, more people live, therefore more people powerlift, and also body weight. More people are towards the lower end. I suspect that is because in powerlifting, everybody wants to be as lean as possible so that their lifts are more impressive for their weight class. We also see multiply. It's very, very rare. Raw, little bit less rare. And single ply is about a 50-50 split. Racks, most do not use straps. And then performance enhancing drugs, most competitions do actually test for performance enhancing drugs. And yeah, that's it. So comparing the 2 sets of models. In the first set of model, which does not omit bench, squat, and deadlift numbers, the decision tree has the lowest mean squared error of any model by a pretty significant margin, meaning that this is the most reliable model that we can go on to use to make predictions. Model 2, similar, but their neural network is a little bit better than the regression models. Something to note is that the variability between both of these is quite different. There is way less variation between the worst model and the best model in model 2 and the model set 2, and there is way more in the model set 1. So breaking down the decision tree for model 1, which was the second most ideal model, this is the ideal path in orange. We go down here, we just follow this little tree down to the ideal path. Obviously, there are more branches, but I just wanted to show exactly what we are going to be talking about on the next slide. Some fit statistics to go into. It is a pretty good model. The sum of squared errors compared to everything else is much lower. And obviously 700 degrees of freedom since the testing variables, since the testing observations are about 700, not about 700, they are 700. In terms of variable importance, you're going to see here that the squat is the most important, which makes sense because people can squat the most. And then deadlift is a little bit less important because I guess people deadlift a little bit less than they squat. From this importance statistics, it seems like that is actually very pronounced. And then bench is less than deadlift, but not as much of a difference as between squat and deadlift. So what does this tell us? Going back to the decision tree, we can see that just following it down on the left here, this describes that path. So to start out, squats at over 132 kilograms, it's about 260 pounds. That creates an elite lifter. That's the most important thing that differentiates elite lifters from less elite lifters. And then the next branch would be deadlifts at over 203 kilograms, about 400, 500, between 400 and 500 pounds, which makes sense. And then the most elite lifters, bench press over 150 kilograms, about 300 or so pounds, obviously less important than the other ones. And then the most elite basket of lifters, pictured here in the darkest blue, squat at over 327 kilograms, at least in this sample, in this random sample, that happens to be the case. It could be more, it could be less, but in this random sample of 1,000, the top 7 lifters all fell into this basket. So this branch only makes up 7 of the 1,000 total observations. So clearly squat numbers drive the highest lifting totals since they were the first in the branch. And then they should be trained the most for a competitive advantage, seeing as people lift the most in squat, and that helps differentiate people most. Perhaps there's synergy with other lifts. Obviously, more further research would need to be done for this to verify that. So going back to the Model 1 decision tree results and output, squat's the most important predictor of a heavy total, followed by deadlifts and then bench. The model omits every other variable, which is important to note due to the importance of the 3, meaning it does not factor in performance enhancing drug use. It does not factor in lifting straps. It does not factor in gender, which is why we needed model set 2 to actually hone in on that. Model 2, the best model was the neural network. If you recall, this graph right here on the left shows the difference between the target and the predicted and the training set. As you can see, there is significant overlap between the two, showing that the model is actually a pretty good fit. Some fit statistics we have here, if you would like to look at that, most important being the mean squared error, which is actually very simple, very similar between the training and the validation set, showing that the model is not overfitting or underfitting the data, which is great. You can rely on this model. Essentially, it would be helpful to have more data, but from what we have, it seems great. So model 2. Now, it's very difficult to actually put the results of the neural network into English. So that's why I brought out this stepwise regression, which was a less effective model, but is easily interpretable and doesn't have that much of a variability from the other models. So stepwise regression shows how each attribute minus the, well, I guess, except for the squat, bench, and deadlift, the totals. So not being tested for performance enhancing drugs, which is right here, increases the totals more than any other attribute. This is according to the analysis of maximum likelihood of fit. And wraps are the most beneficial equipment for higher totals. As you can see, this has the highest absolute value and affects lifts more than anything else. Year is very low in terms of how much it affects it, but it does have an effect. And body weight is the same. Something to note is that it looks like as years progress, people lift less. That might only be in the sample, but it's interesting to note, little interesting observation. But essentially, if you were to run a regression model, this estimate column does show exactly what it would be. So the y-intercept would be 4852.6. The body weight kilograms would be whatever that number is times this, then male, multiply it by that, yada, yada. And that's how you would get the prediction for the lift. So theoretically, you can go in with the body weight, the gender, if we're going binary there, and then not tested for PED, raw, wraps, and year. And then it will actually, from this regression model, spit out an actual number for what it would be, what someone would be expected to lift with a good amount of accuracy. So obviously limitations, SAS Enterprise miner crashes with more than 1K rows. I have no idea why it does that because it hasn't done it in the past. But for this data set in particular, perhaps because it's in the JRP.jrp format, it doesn't like it. So more data would be ideal. And if I was to delve further into this, I would have to reach out to tech support and figure out why in the world that's happening. It would also be interesting to have a country of origin as a variable, because as it's pretty evident, people in Iceland lift a whole lot of weight, a lot more than many other countries. So it'd be interesting to see how that Icelandic nationality variable actually plays in. How many pounds would that add to your lift just being from Iceland? That's obviously limited because there were about 200 countries represented in the data set as categorical variables. So if I was to transform this into binary columns, that would be 200 additional columns, which would clearly crash the data set and would not be able to get any actual data out of that or any model out of that. So that's a little limitation, but I'd like to do that in the future. So in conclusion, if you use performance enhancing drugs or compete in a division where performance enhancing drugs are not tested for, and if you use equipment, you will have a higher lifting total. Pretty obvious, but it's interesting to see the actual niche effects of each piece of equipment. Focusing on squats will increase totals the most, whether it's because that increases synergy or because, squats are obviously the most highly lifted lift. People can lift the most on it. That remains to be seen, but I think could be pretty obvious. Neural networks are ideal for prediction from attributes. Obviously, they have the lowest mean square error, but it's really difficult to interpret actually what is going on in a neural network. And decision trees are ideal for predicting from 3 lifts, including every other variable, but the decision tree that we got literally only had the 3 lifts in it just because all the other variables were not nearly as important for predicting the total, since the total is the aggregation of those 3 lifts. So stepwise regression is ideal for understanding what is going on in these models, because in all honesty, it's quite difficult to interpret what is going on from a neural network, and it is a little bit less difficult to interpret what's going on with a decision tree. So that's all I got. I will look into possibly expanding this in the future, but thank you for your time. Hope you learned something. Obviously use some wraps if you're going to be lifting heavy. Thank you.